Okay, so the goal of today is to start talking about the handle-body decomposition. The main idea is that if you have a manifold, a manifold and a Morse function on it, then the Morse function will help you understand the topology of the manifold. The Morse function will help, the critical points and the behavior of the critical points will help you understand the topology of the manifold and recover the topology of the manifold. That's kind of the basic definition. So using a Morse function, we'll be able to split up our manifold into some building blocks. And these building blocks are relatively simple. Okay, so let's see how we do that. So first of all, maybe I'll start with an observation. Oh, before that, let me just make a definition. I have kind of said that before, but let me write it down. So a compact manifold without boundary is called a closed manifold. Okay, so that's a very common name that's used a lot in topology and geometry. So it's a closed manifold, just means it's a compact manifold without boundary. And often when people say a compact manifold, they mean that the manifold could have boundary. Okay, so that's just the standard name. It's a little confusing because, of course, a topological space is always closed in its own topology. And also you can have submanifolds of other manifolds that are closed as subsets, but they're not a closed manifold. So the language is a little confusing, but it usually doesn't create very much confusion. So usually you just say, let X be a closed manifold, independent of anything, what we were talking about. Okay, so my observation is that let's fix X a closed manifold. And F a Morse function. So for each regular value, A and R, we can define a manifold XA, which is the preimage of -infinity A. Then this XA is a compact manifold with a boundary given by the preimage of A. So this is something that we saw at the beginning of the course. This is basically follows from the implicit function theorem. So moreover, because X is a compact set, the image of F is compact. So this XA is empty for A very small, and XA is the whole space for A very large. So, if, for example, if I have a Morse function like this, so I have a genus 2 surface, and I think of it embedded in R3, and my Morse function is the height function, as usual. So this MA is, if I fix an A here, a regular value, my MA is this manifold, the preimage of -infinity A. So what is interesting is I can vary this A along R, and what I can say is if A is very small, so it's below the minimum of the function, then this xa is empty. And if A is very large, above the maximum, then xa is the whole manifold. So in a way, if I want to reconstruct the manifold, I could think about what happens with xa as I vary, as A goes between the minimum and the maximum of the function. And that's the main idea of this hand-the-body decomposition. I would say that's the main idea of Morse function, is to look at these manifolds xa for varying A. Okay? Any questions about this? Okay, so the first result is a proposition. I'm going to call proposition. It's the following. So let X be a closed manifold. And F a Morse function. So suppose that the interval AB does not contain any critical values. So suppose all the numbers between A and B are regular values. Then the manifold XA is diffeomorphic to the manifold XB. Okay, so that's the first result. And you can see that maybe from this picture is if I move the A, if I choose another point B over here, and you see that between these two, there is no critical value. The critical values are the images of the critical points. Over here, I have 6 critical values. But if I take an interval that contains no critical values, the claim is that this XA is diffeomorphic to XB. Let me emphasize, this is a diffeo. Okay, so let's prove this. Any questions about the statement or what I've said so far? Okay, so the idea is to use a vector field, the flow of a vector field, to find the diffeomorphism between XA and XB. Okay, so how do we do that? Well, we have to choose a vector field that basically increases F or decreases F. Okay, so what is such a vector field? Well, I think you're very familiar with the gradient vector field. Although maybe if you haven't taken Riemannian geometry, you're not so familiar with it. I've mentioned something about it before, but let me say something a little more general. So something more general than the gradient vector field is what's called a gradient-like vector field. So a gradient-like vector field, V, is a vector field such that the zeros of the vector field are the same. So sorry, a gradient-like vector field, it's a gradient-like vector field for a specific function. So I have to say that it's a gradient vector field for F. So it's a vector field such that the zeros of the vector field are the same as the critical points. They're the same as the critical points of F. And the directional derivative of F in the direction of V is always positive whenever, let's say, Vx of F is 0 if X is not a critical point. Okay? So it's a vector field that increases the function. That increases the value of the function. That's what a gradient-like vector field is. And an example is the gradient vector field for a fixed Riemannian metric. So an example is if G is a Riemannian metric, no, let's not call it G. Let me just call it bracket like this. So this is an inner product at every point, every tangent space. If this is an Riemannian metric on X, there exists a unique vector field, which is called the gradient of F, such that when you put the gradient and you leave the second input blank, this is the same as doing df. Okay, and you can check that the gradient of F is a gradient like vector field. Okay, so now if you can the thing about gradient like vector fields is that you actually have more freedom, a lot more freedom than a Riemannian metric. You can change the vector fields even more than looking at gradient vector fields. But for the purposes of this proposition and what we're going to say after today, you might as well just always consider the gradient vector field for a given Riemannian metric. Okay, but I thought it's a good idea to know to have heard of this term gradient like vector field before. So yeah, so now I'm going to define. So I'm going to try. So I was just doing a definition. Now I want to prove this diffeomorphism. So to do that, the idea is to use the flow of V to find the diffeomorphism. To find the diffeomorphism from XA to XB. But the flow of V, V, the derivative of V in the direction of F, the derivative of F in the direction of V is positive, but it could vary widely from point to point. So what we actually want to do is we want to define a vector field that's V divided by VF. Okay? But the problem is that this vector field is, so this is a normalized vector field, a normalized gradient-like vector field. But the problem of this is that it's not defined over the critical points. So you have to be a little bit careful. And what we do to be able to do that is we choose a bump function. So we would like to do that. We would like, but this is not a global vector field. So instead, we choose a bump function. So let psi is a bump function such that it's identically equal to 1 on the pre-image of AB. This is going to be a compact set because X is compact. I want the support as usual, and the support is compact. And I mean, you could say, for example, that the support is contained in the pre-image of A minus epsilon and B plus epsilon. But all that we really need is that the support of psi does not intersect the set of critical points. Okay, so I know that, I assume that A and B, that this pre-image here does not contain any critical points. So because the set of critical points is isolated, I can always choose a psi like that. Okay, so for example, you could assume that the support is contained in the pre-image of A minus epsilon and B plus epsilon, for epsilon sufficiently small. Okay, so now we can define W X to be the following. I can do psi of X times Vx over Vx F if X is in the support of psi and 0 otherwise. Okay, so yeah, so this W is now a vector field on all of X. And since X is compact, W has a global flow. Phi t for all t. Remember, the flow is basically the integration of the vector field. So the flow satisfies the property that ddt of phi t of x is equal to the vector field at the point phi t of x. Okay, so now let's see what happens with the function f as we go along the flow. So if I look at f applied to phi t of x, what's the derivative of this with respect to t? Well, by the chain rule, this is just going to be df at phi t, at w, phi t at the derivative of the flow. So df of w phi t of x. But this is the same as df of v over vf, which is the same as df of v. So this is 1. Sorry, that there's a psi. This is equal to psi of x times df of v x over vx of f, which is just psi of x. Okay. So that means, in particular, ddt of f of v of this derivative is always a number between 0 and 1. And if phi t of x is has an image between a and b, then this derivative is actually equal to 1. Okay, so let me draw a picture just to explain, better what we're trying to do. So let's say that we have this, I don't know, this torus or something. Doesn't really matter what happens above, but this is the level A, this is the level B, and then I have my gradient-like vector field that you can think about as just being the gradient. So I normalize it, and then now by normalizing it, what is happening is that the function is increasing at constant speed 1, at least in this interval. And of course, I have to use its bump function because this is not going to be well defined near the critical points or at the critical points. So basically, you can think about it as like over here, my vector field is 0, so it doesn't do anything, and then there is a bump function using to connect the 0 to this thing that has kind of constant speed 1 with respect to f. Okay, so that's the picture. So now I claim that phi b minus a of xa equals xb, and phi of a minus b of xb equals xa. Okay, so if I flow positively in time b minus a, this will take xa to xb. And if I flow negatively with time a minus b, this will take xb to xa. Okay, so so let's prove this. So let's suppose x is in xa. Now let's see what phi of b minus a of x, where this belongs to. Okay, so we yeah, so we have to compute, I think this, and that's the easy part. So what is f of phi b minus a of x? That minus f of x is the integral from 0 to 1 of d dt at t equals s of f of phi t of x. This is just the fundamental theorem of calculus, ds. And this is equal to, well, here, this is going to be less than or equal, this thing in here is going to be less than or equal to 1. So this is less than or equal to the integral from 0 to 1 of 1 ds. Oh, sorry, this is the integral from 0 to b minus a. B minus a. And this is b minus a. So this means that, yeah, this difference is less than or equal to b minus a. So since f of x is in xa, f of x is less than or equal to a. So this means, this implies that f of phi b minus a of x is less than or equal to b. Okay, so we actually have that this so phi of b minus a of xa is contained in xb. Okay, we actually don't need to prove the equality. But now what we're going to do is we will prove that phi of a minus b of xb is contained in xa. Okay, and then because phi of b minus a is the inverse of phi of a minus b, then these both have to be, this is going to have to be a diffeomorphism. And the images are going to be equal. So maybe I should just say the claim is that this is contained here, and this is contained here. And because these are flows, we know that one is the inverse of the other. So yeah, when you apply this and you apply this, you have to be the identity on xa, and vice versa for xb. Okay, so let's prove that. This is a little bit harder, but not a lot. So the first thing to notice is that it's easy to see that phi a minus b of xa is contained in xa, right? Because this is negative, and the derivative ddt of f is always positive. This is because ddt of phi t is bigger than or equal to 0. So if I take it the time, a negative time, sorry, of f of this, then it has to decrease the value of f. Okay, so if I have something that has where the f is less than or equal to a, then when I apply the flow, the f is going to be smaller. Okay, this is because, let me just write it like this. Phi of a minus b, f of this minus f of x is the integral from 0 to a minus b of, yeah, or if you want, maybe it's better to say this is minus the integral from a minus b to 0 of psi of phi of t dt. And this thing is always greater than or equal to 0, so this is going to be less than or equal to 0. Okay, so that means that f of phi a minus b of x is always less than or equal to f of x. Okay, this is because the time is negative. Okay, so if this is less than or equal to a, then this is going to be less than or equal to a. But now the thing that's interesting is to show that if I actually am between a and b, then when I apply this phi of a minus b, I still am going to be less than a. And now we have to use the fact that this psi is actually equal to 1 in this interval. Because if psi was smaller than 1, then I wouldn't be reducing fast enough. So I kind of want to reduce at the speed 1 so that when I use, when I'm at time a minus b, then I actually go all the way below a. Okay? So now we just have to write this down. But maybe maybe now you would be able to do this. But so first of all, so let x be a point in the pre-image of AB. So now let's fix time t in a minus f of x 0. Actually, let's not be so confusing, and let's do positive times and then just slow with minus t. That might be a little more orienting. So let's take a t that's between 0 and f of x minus a, and we're going to flow with time minus t. Okay, so now what happens is, so f of phi minus t of x minus f of x is equal to the integral from 0 to t of dd s at times s equals u of f of phi s of x du, minus the integral from minus t to 0. And then this guy is less than or equal to 1. So this is going to be greater. Yeah, this is less than or equal to 1. So this is going to be greater than or equal to minus 0 minus t. So greater than or equal to t. Sorry, this is what happens when you change from your notes to the class. Yeah, this is the psi of phi u of x, and this is less than or equal to 1. So this is going to be bigger than or equal minus 1 minus t. Yes, that's right. Yeah. So sorry, I'm confused again. This is less than or equal to minus 1. So this is going to be greater than or equal to the integral from minus t to 0 of 1 dt, which is equal to t. Well, I think what I want to say is f of x minus f of this. Sorry, guys. This is, I am really, I prepared it and then I changed the direction of my gradient. So then I'm getting minus signs all over. So f of x minus f of phi of minus t of x is the integral from minus t to 0 of dds of s equals u of f of phi u of x du. So that's the integral of psi. Okay, let's do it like this. So this psi is of phi u of x du. Okay, and this is less than or equal to 1. So this is going to be less than or equal to the integral from minus t to 0 of 1 du, and that's equal to t. And t is less than or equal to f of x minus a. So this implies that f of phi of minus t of x is greater than or equal to a. Okay, that's what I wanted. Okay. So what I'm saying is that if I start with something whose image is between a and b, and then I apply the flow at times minus t for t between 0 and the difference between the image of x and a, then I'm still in this interval. So that means that phi minus t of x is still in the pre-image of AB. Okay. I know by this first argument that this is still less than or equal to b, because when I apply the flow for a negative time, I have to be going down. Okay, but the point is that I can't go down too fast because I have this bound that the psi, the derivative of f, is bounded by 1 above. So it's bounded by 0 below, and it's bounded by 1 above. So I have to always be going down with the negative flow, but I can't be going down too fast. So that's what I'm doing. So what I'm saying is, again, if this is b and this is a, and I pick something here, then if I apply this time, I cannot be going faster to get out of a in time less than f of x minus a. Okay, and in fact, I'm going to go exactly at the speed 1. So because phi minus t of x is always in this interval, then psi of phi minus t of x is equal to 1. So now what I can say is that if I actually take the flow at times minus f of x minus a of the point x, the image of this by f is going to be exactly equal to a. Okay, so if you don't believe that, I can do the calculation. The calculation is basically the same as here, but except that now the psi is equal to 1. So f of x minus f of this at the point phi of minus f of x minus a. So at this time, at the point x, so this is the integral from minus f of x minus a to 0 of dds of this. So this is just the psi of phi t of x dt. And we proved that this guy is the psi is always equal to 1 for t between 0 and minus f of x minus a. So this is equal to 1. So this is going to be equal to f of x minus a. So therefore, phi of this, the image of f of that is equal to a. Okay? So, this is exactly what I was explaining with this picture. If I start at a level f of x, so x goes to f of x, and I apply the time and I flow backwards with time f of x minus a, then I arrive exactly at a. Okay? So now, if I flow with time minus b minus a of x, this is the same as flowing with time minus b minus f of x, and then composing with flowing with time minus f of x minus a. Okay, so I just proved that, this is equal to a, so the value of the function is equal to a, so this guy belongs to xa. It's in particular less than or equal to a. And I know that if I flow negatively, something in xa, it's going to continue in xa. Okay, so the conclusion is, hence, if I flow with time minus b minus a, xb, I actually am contained in xa. Okay, so since phi of b minus a composed with phi of minus b minus a equals the identity, and that also equals phi of minus b minus a composed with phi of a of b minus a, we have the desired result. Okay, so we have two sets. One is taken to the other and the other is taken to the one, but these two maps are inverses of each other. So that means that phi of v minus a is a diffeomorphism from xa to xb. Okay, so that's the end of the proposition. Okay, any questions about this? So I had originally prepared this using the negative of the gradient, or negative of the of a gradient-like vector field. But then here I did the plus, so the calculations, you got a bunch of minus signs, and I don't think there was any mistake here. But it's always tricky to change signs, so be careful. Okay, so is there any questions about this?
Eu tenho uma pergunta. A gente não precisa nenhuma propriedade muito especial da função C-Morse, né, para essa demonstração. Tipo,
não.
Além de os... Certo.
Não, só a função C-Morse é o suficiente.
Mas tipo, você poderia fazer com uma função que não é Morse? Tipo, sei lá, tipo, que os valores críticos são isolados, por exemplo.
Na verdade, você não precisa nem que a função, nem que os valores críticos são isolados. Você só precisa dizer que você só precisa de um intervalo que não tem valores críticos. Na verdade, sem razão. Você poderia pegar qualquer função e um intervalo onde você só tem valores regulares. Um intervalo onde você não tem valores críticos, e essa demonstração também valeria. Exatamente. Yeah, so in fact, you're right. Like the proposition, I assumed that f was a Morse function, but I didn't have to assume that at all. I just did that because that's our setup, and we'll see that this is kind of the first step. But yeah, it's true that the proposition holds for any smooth function, any f smooth function, such that AB doesn't contain critical values. Yeah, that's true. But the point is that the next thing now, maybe this proposition is like the step one in understanding how the topology of X changes as we go through A. But the problem is, if the function is not Morse, then you're completely hopeless when you go through critical values. So in particular, you could have, the critical values don't even have to be isolated. But the point is that now we actually fix Morse function. Actually, before I continue, are there any other questions about this proof? Mais alguma pergunta sobre a demonstração? Não.
I didn't understand the part about the gradient vector field, but maybe I can ask it at the end of the class.
No, I can say it now. The gradient vector field or the gradient-like vector field?
The gradient-like vector field, sorry.
What did you not understand?
So the condition is that like the derivative of the function is positive in the direction of the vector field.
Yes.
That's all you ask.
Yes, that's all I ask.
And if you have a Riemannian metric, you just take like the connection, something like that.
No, you don't need a connection. If you have a Riemannian metric, there is a vector field, which is called the the gradient vector field, and it has this property. It's dual to the f using the Riemannian metric.
Okay.
And you have I guess you want to check this property for the gradient. So how do you check this property? Let's so say that you have the gradient vector field, and you know that it satisfies this property. That's the definition of the gradient vector field. So let's call this V. So what is VF? VF is the same as dF applied to V. So dF applied to V is going to be the same as the gradient of F applied to the gradient of F. Okay, so this, but because the norm, the Riemannian metric is positive definite, then this guy is equal to 0, is positive. Whenever it's not 0. And you know the gradient is 0 exactly at the critical point of F.
Okay.
Okay.
So it always exists because of that.
Yeah, exactly.
Thank you.
But the point is that it's easier to modify a vector field, a gradient like vector field than the gradient. Because if you want to perturb a gradient like vector field, it's very easy. You keep it at the critical points, and you can perturb very easily because this condition is open. The condition of VF being positive is an open condition. But if you want to perturb the gradient vector field, then you have to perturb the Riemannian metric. So it's a little bit more complicated. But actually, it doesn't matter for this proof. You can just take the gradient. Yeah, so I heard some activity. Maybe people just came in. Yeah. Okay. No messages. Okay. Any other questions about this proof? I mean, this proof is just, using the flow. I guess there are 3 keywords: using the flow, the fundamental theorem of calculus, and using a bump function. Okay, so can we keep going? All right, so now we fix a Morse function on your closed manifold with the property that we proved from last time. So with the property that if the critical points are P1 through Pn, then they all have different images. So the critical values correspond to a unique critical point. Okay? So what is this telling us? So together with this previous proposition, this is saying that if you want to analyze XA for different values of A, there really are only n or n plus 1 different possibilities. So in the intervals between the critical values, there's no change. So what we have to analyze, so if I take an A that's less than, and let's also assume, just for simplicity, that these are ordered by the value of the function. Pm. Okay, so if A is less than f of P1, then XA is empty, so that's the minimum of the function. If A is bigger than f of Pm, then XA is the whole manifold. So it remains to understand what happens with MA as with XA as we cross a critical value. Okay, so what's the question, I guess, is what is the relationship between x of f of pi minus epsilon and x of f of pi plus epsilon? So that's the question that we're going to answer now. Okay? So before that, we can say what happens as you cross the smallest one, f of p1, and you can say what happens when you cross the largest one. So that's going to be the easier part. So p1, so first of all, let's look at p1. So p1 is the minimum of f. So it's going to be a local minimum in particular. So it has the index of p1 is 0. Okay, so it's the Morse index is 0. So in a chart, we can write, or in a Morse, it's called the Morse chart. We can write f of x as f of p1 plus the sum of xi squared from 1 to n. Okay, so if epsilon is small enough, is greater than 0, is sufficiently small, then it's kind of clear that f of p1 plus epsilon is contained in the domain of this chart, in the domain of the Morse chart. Okay, just because of continuity, because p1 is an isolated minimum. So if everything, if the value of the function is less than or equal to f of p1 plus epsilon, then you have to be contained in a neighborhood of this point. Okay, so now the problem is easy, because if this is contained, this x of f of p1 plus epsilon is contained in the Morse chart, then in this chart I just have to see what is the set of points such that f of x is less than or equal to f of p1 plus epsilon. And this is the same as saying that the sum of xi squared from I equals 1 to n is less than or equal to epsilon. So this is if and only if x belongs to a ball of radius epsilon. So this epsilon here is the radius. Sorry, square root of epsilon. Okay, so then x of f of p1 plus epsilon is diffeomorphic to an n ball. Okay, so you see what happens when you go through the minimum is that if you're below the minimum, then you have the empty set. And if you just go a little bit above the minimum, then you have an n-dimensional ball. That's the change of the topology. Okay, so as we go through the minimum, sorry, I have to say this p1 is not the minimum value of the function. P1 is the minimum point. So it's the point where the function attains its minimum value. So as we go through a minimum value of f, mxa, goes from the empty set to the n-dimensional ball. Okay, so that's what happens. And similarly, it's easy to see that the pre-image of Pm minus epsilon and infinity is also diffeomorphic to an n-dimensional ball. So like applying the opposite, if you change the signs on everything. So if you look at the maximum is going to have index n equal to n, and this is going to be a sum, but with a minus sign in front. And we also get a ball. If you look at sort of the pre-image from a little bit below epsilon to plus infinity. So this means that if you look at x pm plus epsilon, which is just your x, this is going to be equal or diffeomorphic to x pm minus epsilon union some ball. Okay, so of course there is some kind of gluing here. So you're gluing the boundary of the ball to the boundary of this x pm minus epsilon. But anyway, that's what it is. So let's see some examples. I guess this is a good time to stop for some examples. So, well, maybe again, like our nice example, you can look at the torus and you can understand what's going on. So here's P1, P2, P3, and P4. And they have, images A1, A2, A3, and A4. Sorry, I actually, this is x of f of Pm. Okay, so if you look at, x of A1 minus epsilon, this is going to be the empty set. And if you look at x of A1 plus epsilon, this is just going to be this ball. Okay, so this, you see, is a B2. And this is just this first fact that I showed you using the Morse lemma. And similarly, if I look at a neighborhood, if I look at x of A4 minus epsilon, I don't know what it is yet, or I'm not based on this, so you can see what it is. But what happens is if you add, it's just missing a B2 to get the whole thing. So this is going to be equal to AX of A4 plus epsilon. Okay, so my two ball here is this two ball here that I'm adding to what I had left to finish up the manifold. So if I'm trying to split the manifold in pieces, what I can say is, well, let's choose, you can fix a regular value in between each of these guys. And you say, well, I know that it doesn't really matter where I cut, so I just want to see what this piece is, what this piece is, what this piece is, and what this piece is. And when I glue these pieces together, I'm going to have my whole four manifold. So sorry, my whole manifold. Okay, and what I already told you is that the piece corresponding to the minimum and the piece corresponding to the maximum are pretty easy to understand. They're both n-dimensional balls. Okay. Now we have to still, do this procedure, which is seeing what happens when you go from f of pi minus epsilon to f of pi plus epsilon. Okay. Any questions about this so far?
Não precisa ser o máximo nem o mínimo, não. Qualquer um que tem esses índices do máximo e do mínimo teria esse comportamento.
Exatamente,
Então a questão...
Basicamente, Só que o problema é que você não vai poder dizer que o f que o x de f de P1 mais epsilon é isso daqui, né? Porque você pode ter outras partes desconexas. Outras partes que estão longe desse ponto crítico. E sim? Entendeu?
Não.
O que você pode dizer é que uma vizinhança se você tiver um ponto, digamos que o PI, suppose that PI has index 1, has index 0. So what happens is you can't say that f of pi plus epsilon is equal to ball. You can't say this in general, because so you know that in a neighborhood of pi the function looks like f of pi plus this sum. So yeah, in a neighborhood of pi, the intersection of this guy with a neighborhood of pi is indeed Bn. But this manifold here could have other parts. So let me give you an example. So
I see.
You see? So like if you have, I don't know, something like this. And say this is your P1, this is your P2. So when you look at, f x of f of P2 minus plus epsilon, then you're going to be at a level here. So you're going to have this piece and this piece. You see?
Yeah. Locally, we have a ball.
Locally you have a ball, but you could have things that are far away. They have no idea what they are.
No control, yeah.
No control. But what you can say is that going through pi, that x of f of p2 minus epsilon, you actually have the disjoint union with a bn to get to f of p2 plus epsilon. This you can say.
Ou seja, adiciona uma bola.
Yeah, adiciona uma bola. And this is because if you're far away from P2, then you have no critical points, so you can actually consider the same diffeomorphism. You can consider the flow in the same way. So like, if you go from below the image of P2 to above the image of P2, what's outside of the neighborhood of P2 is you get a diffeomorphism in the same way as before. And near P2 is the only place where the topology really changes. And you see that near P2 it changes from the empty set to the ball. Okay?
Então, a ideia do teorema de Morse é, se eu pegar uma função bem especial, que é a de Morse, eu vou ter os pontos críticos, eu vou cortando a variedade, e eu vou, com o índice, eu vou tentar descobrir o que eu adiciono.
Exatamente. E o próximo passo agora é ver o que acontece, quando a gente passa por um ponto crítico onde o índice não é nem zero, nem o máximo. Nem zero, nem n. O que acontece quando a gente passa, por exemplo, por um ponto crítico de índice 1? O que acontece?
Então, os índices vão me dizer o que eu tenho que adicionar à parte anterior.
Exatamente. Okay, so let's go to the crux of the class today, which is to see what happens when we go through a critical value corresponding to a critical point of index k for some k. So now let's let A be the image of some critical point, pi, and k be the index of pi. So again, by the Morse lemma, near pi, we can write that f of x is equal to A minus the sum of xi squared from 1 to k plus the sum of xi squared from k equals, well, let me actually save, I'm going to use x for something else. I'm going to write f of x1 through xn. So from I equals k plus 1 to n. Okay, so in a chart where I take pi to go to 0, I have that the function has this behavior. Okay, so I'm going to actually write Rn as the product of Rk with Rn minus k. So the function, I can think of the function as having two coordinates, x and y, x is in rk and y is in r minus k, and this is a minus the norm of x squared plus the norm of y squared. And I'm trying to understand how x a minus epsilon becomes x of a plus epsilon. Okay, so let's look, at the neighborhood of this point. I'm going to draw the picture, and this picture, it makes sense for n equals 2. The picture is for n equals 2 and k equals 1, but you can draw a similar picture for n equals 3, and you can kind of understand what's going on in general. So let me try to draw this picture. So I don't like this one. Okay, this is horizontal enough. Okay, so this is, sorry, I'm kind of drawing slowly. Now I want to draw. So I'm going to draw. It's supposed to be a hyperbola. I'm sorry for my picture, but this is supposed to correspond to the pre-image of a minus epsilon. And this is another hyperbola, which is supposed to correspond to the pre-image of a plus epsilon. And then now I'm going to take my Morse chart, which is yes, good. So this is my U, my Morse chart. Okay. So, this point here is my point pi, so that's 0. And the value of the function here is a. So what I'm trying to understand is how the topology of, what's less than a minus epsilon, which is kind of what's inside this hyperbola here, and what's less than a plus epsilon, which is what is inside all of here. Maybe I want to... Yeah, I'm not going to write this to not clear the picture too much, but you see where this x of a minus epsilon is and where the x of a plus epsilon is. Okay, so what I want to do now is I want to consider a set that I'm going to call H. And the set is going to be the set of xy such that well, it's going to be I'm going to look at what's between the two. Yeah? So this is the pre-image of a minus epsilon, a plus epsilon, intersection with what's inside this, inside this chart, so x and y, such that the norm of x times the norm of y is less than delta for some small delta. So if delta is sufficiently small, I can assume, I can get that this H is contained in U. So my H is going to be something like this. Okay, so this is my H. Okay, so why am I doing that? So I'm isolating on a very, very small thing, this H, really all the action. Because outside of this H, it's not hard to see that what I have, I can actually apply that flow, and I'm going to have a diffeomorphism. Okay, so I'm going to explain that in a little more detail. But let's try to understand what this H is. So first of all, let's start with some interesting claims. The first thing is, what is the intersection of H with the pre-image of a minus epsilon? So can someone tell me what this is? Can you see what it is? Well, in this particular picture, I have these pieces of the blue part. These pieces of this blue hyperbola. But the claim is that this is always, given a k and given an n, this is always diffeomorphic to s k minus 1 times b n minus k. Okay, so why is that? Well, we can actually write down the proof. So you want this guy to be equal to a minus epsilon, and then you want this condition to be satisfied. So the proof is the following. So when you write this thing, this is the set of x, y such that x squared minus y squared is equal to epsilon, and norm of x times norm of y is less than or equal to, I want to put the boundary, less than or equal to delta. Okay, now, if you want, this is a simple exercise in, I don't know, it's not really linear algebra. There's no analysis either, but it's just in higher dimensions. But let me do this for you, because maybe this is so many dimensions you're getting a little confused. But this is kind of simple. You see that you have complete freedom on y to go all the way to 0. So what I'm going to do is you can actually figure out what the maximum radius of y is to satisfy this. So the maximum radius, I did the calculation. This is minus epsilon plus the square root of epsilon squared plus 4 delta squared over 2 to the 1/2. And then now you can define a diffeomorphism. You can define an embedding that goes from sk minus 1 times the ball of radius r max into your rk times rn minus k. That takes x and y to epsilon plus norm of y squared to the 1/2 times x and y. So anyway, it's not very hard to see that this psi is an embedding, and it's kind of obvious that it's an embedding, and that the image of this guy is exactly equal to the domain in question. So I'll let you verify this. This is now a simple calculation. But I think the point that's kind of interesting is, like, looking at this picture, what's happening? So if you set y to be equal to 0, what you really have is you have an sk minus 1. So if you set y to be equal to 0, then you just have the set of points x such that norm of x squared is equal to epsilon. So that would correspond to this point here. I mean, in this picture, it's 2 points. But if the k was bigger than 1, then you would have a higher dimensional sphere. So this, maybe let me draw it light blue. I don't have so many colors here. Pink. So this pink thing is an sk minus 1. And if I actually want to get the whole intersection of h with the preimage of a minus epsilon, then I have this sk minus 1 times a disk in dimension n minus k. So this thing here in pink, more pink, is sk minus 1 times b n minus k. Okay, so that's the part of h that intersects the preimage of a minus epsilon. And similarly, what's the intersection with a plus epsilon? Now maybe it's not so hard to see, but similarly, if you intersect h with a plus epsilon, what you get is something that's diffeomorphic to bk times s n minus k minus 1. Okay. I mean, in our picture, because n equals 2 and k equals 1, they look the same. But I mean, it's not hard to even think about rotating this around, and then you're going to have a picture where k equals 2 and n equals 3, and then the two things are a little bit different. And the two hyperboloids, one is a hyperboloid with one sheet, and the other is a hyperboloid with two sheets. And in general, you're going to have these generalized hyperboloids in Rn when you fix a k between 0 and n. Okay, so is this picture clear, the description clear so far? I want to go very slowly because this is kind of the most crucial point of the handle decomposition. So please ask me.
Professor,
Oi.
Não estou entendendo muito bem essa imagem. O que é? Ela é tipo ela é as curvas de nível da função?
Na verdade, eu não desenhei todas as curvas de nível, né? Eu desenhei duas curvas de nível, né? Que é a curva de nível de A menos epsilon, a curva de nível de A mais epsilon. Né? E agora, o que eu estou fazendo é que eu estou cortando o que? Let me maybe say one more step. What I'm doing is so maybe I should draw this. This blue guy, I'm going to erase it later, is x A minus epsilon. This is what we had before going through, we're getting very close to A, and then we have this blue guy. And then when you go above, through A plus epsilon, then you get that added with all this. Okay, so what we're trying to see is how the blue guy becomes the red guy. And what I'm saying is that, well, what I will say is that I'm gonna add two parts. So I'm gonna take the blue guy, I'm gonna add the H, which is this light blue thing. And then I'm gonna add something else, which is I'm gonna call the R. So this is R. Okay, so my R is going to be, if you want, I take the pre-image of A minus epsilon, A plus epsilon, and then I subtract H. And let me just take the closure. I want the closed guy. So the point is that by construction, x of A plus epsilon is equal to x of A minus epsilon union H union R. Okay, let me go back. So you see, to go from A minus epsilon to A plus epsilon, what I have to do is I have to add H and I have to add this R. But the point is that the R is actually easy. The R, as I'll say in just a few minutes, the R, there's nothing going on with R. There's nothing very interesting going on with R. R is just a product. Okay?
Uma pergunta.
Fala.
Então, o eixo que está na horizontal seria o RK, o que está na vertical o RN menos K, é isso?
Yeah. Sorry, I forgot to label, but I thought that was kind of obvious.
Não, só para melhorar um pouco do exemplo.
Tudo bem, posso esperar mais um pouquinho, todo mundo absorver.
Professor?
Fala.
E o que seria as assíntotas nessa figura?
Isso seria o quê?
As assíntotas na figura ia ser o quê? A assíntota da hipérbole, o x que passa pela origem.
A assíntota da hipérbole?
Uhum.
A assíntota da hipérbole é exatamente o conjunto, é a pré-imagem de A.
Tá.
Né? É x squared minus y squared equals 0.
Uhum.
Uhum.
Então essas duas curvas de nível vão meio que convergindo nessa assíntota? Conforme a gente vai diminuindo o epsilon?
Exatamente. Uhum.
Ah, legal.
Que é o que você imagina, né? Quer dizer,
Uhum.
eu tô desenhando uma foto das consequências dessa fórmula daqui, né? My function is A minus the norm of x squared plus the norm of y squared. And I'm just drawing a picture to help you understand what I'm doing, but I'm actually doing everything in dimension n directly. But if you want to do it, more slowly, you can just do this for the case n equals 2 and k equals 1. And then the picture is exactly this picture. Okay, but what I'm doing here, holds in any dimension.
So this describes the topology of every manifold?
Well, it will, but I haven't told you very much about what H is so far.
Okay.
Yeah, I mean, sure, you can say, for now, you can break the manifold into these pieces where you have the critical value, one critical point in each piece, and they glued. But so far I haven't told you what H really is. I'm just telling you some properties of H, and there's this other R, which but eventually the goal is to say there's a building block, and this H is the building block. And it's going to depend basically only on K and N and nothing else. Okay? But that's where I'm going, but I haven't gotten there yet. Okay. So now, the next thing I want to say is that this R is basically trivial in a sense. So this R is basically a product. And why is that? Well, it's not crazy to think that the next thing I'm going to do is I'm going to look at outside of H. I can look at the flow of a gradient-like vector field. So this is kind of light, but I can consider a gradient-like vector field, V. And for example, you can take just norm of F. You can just take the gradient of F over the norm of the gradient for a Riemannian metric, which is Euclidean in U. So you can do this. You can choose the Euclidean Riemannian metric on U, and then you can extend it to a Riemannian metric elsewhere. But the reason I want it to be Euclidean is because I actually want to compute the gradient of F using this expression. And using this expression, the gradient of F is just going to be minus 2x and 2y. Okay? So an exercise is if you look at the flow, if phi t is the flow of V, then phi t is going to map, phi t of the boundary F inverse of A minus epsilon. When you remove H, that's going to be F inverse of A plus epsilon removed H. And this R is diffeomorphic to this guy times the interval 0 to epsilon. Sorry, this is right at time 2 epsilon. Okay, now I have to go back and forth between the picture. I wish I could keep the picture somewhere, but I can't quite do that. So what I'm saying is, if you remove this part of A, the intersection of the levels, the level curve or this level hypersurface, A minus epsilon, if you remove the intersection with H, then you can apply the flow of V, and you're going to get exactly what you get with at the level curve of A minus epsilon. Remove the intersection of H. Okay, and moreover, this flow is going to be it actually is tangent here. So this is a simple flow calculation. You just look at the flow of the gradient, and yeah, that's it. Okay, and when you renormalize, you don't change the flow lines. So you know that it has to go from A minus epsilon, from the level curve A minus epsilon to the level curve A plus epsilon, because you divided by the norm of the gradient, so it's a normalized gradient. So after time 2 epsilon, it goes from here to here, and then you you also, it's easy to see that it's not, if this condition here is not satisfied, then it's not going to be satisfied when you do the flow, because the flow preserves the norm of x and preserves the norm of y. Okay, so that's something simple to check. But you can just look at this again. You can check everything in higher dimensions, but if you're a little confused by higher dimensions, you can just look at this picture and you can do everything in the picture, at least for the case k equals 1 and n equals 2. But I'm trying to do all dimensions at the same time. Okay, so the point is that you see this R is just this set. Oh, well, maybe let me draw the picture again so you see what. So when I remove my H, so if this is H, R is just going to be, this guy times a fixed interval, 0 to epsilon. Okay, so now I have to, now we're almost there. So we know that x of a plus epsilon equals of xa minus epsilon union H union R. And this R in some way is kind of trivial. So let's formalize this idea a little better. So let me just tell you that H and R, these are manifolds with corners. That just means, a manifold with corners is just a manifold where the charts have values, take values, in R. If you just take the half line and you take the product n times, so that's like the first quadrant of R to the n. So you have these corners. So the H. It's something that only makes sense in the world of smooth manifolds, because if you're a topological manifold, then a corner doesn't mean anything. It's just a piece of the boundary. But smoothly speaking, there is such a thing as a corner. So you have this part, and then you have this part, and this thing here is a corner. So a chart over this point is something that's modeled in the first quadrant. So this point could be taken to this point, could be taken to this point, could be taken to this point. These are different kinds of corners. I don't want to talk too much about corners, but the point is that there are these things called corners, manifolds with corners, which is where the chart has values, takes values in a quadrant. So you not only have like a boundary point, but you also have points where you actually have a corner. This is not diffeomorphic to a boundary point. But anyway, the thing is that even though H and R are manifolds with corners, when you glue H and R, that becomes a manifold with boundary that glues to another manifold with boundary to give rise to a manifold with boundary. Okay, so H and R have corners, but when you consider the union of H and R, this does not have corners, or this is a manifold with boundary. This is a smooth manifold with boundary. Okay? Okay, any questions about this? So now what I'm going to do is basically I'm going to squish this 0 to epsilon direction. So I'm going to compress it to 0. So I'm going to create a equivalence relation. So now I'm going to define an equivalence relation. An equivalence relation as follows. So if x equals yt in R, okay, sorry. I'm going to define it like this. So first of all, y1, yeah, yt1 is equivalent to yt2 for yt1 and yt2 in R. So that's the first thing I do. So, you know, basically, I'm taking this whole line and I'm squishing it to a point. Okay, so clearly when I do, when I mod R by this equivalence relation, all I'm doing is I'm getting rid of this product part. This is just F inverse of A minus epsilon. Minus H. Okay, so I end up with just this part, something that's homeomorphic at least to just this part. I'm just quotienting out by this direction. And then I'm going to do the same thing just with this part of H here. So on H, I'm going to define this relationship like this. So if I have x1, y1, and x2, y2 in H, I'm going to say that x1, y1 is equivalent to x2, y2 if, first of all, they are kind of on the boundary of H, but with respect to delta, the definition. So if norm of x1, norm of y1 equals norm of x2, norm of y2 equals delta, and norm of x1 equals norm of x2, norm of y1 equals norm of y2. No, sorry. No. Sorry. Let me say something else. If x1, y1 is equal to e to the t, x2, e to the minus t, y2. Sorry, this is what the condition I want for some t. So what I'm saying is, on this picture, you know, remember that I had the flow. That's kind of all I'm doing is I'm quotieting by this flow. So all these points here are going to be taken to one point. Okay, so all these points here are going to be taken to one point. But, you know, in higher dimensions, this is not one point. In higher dimensions, this blue thing actually corresponds to an sk minus 1 times an sn minus k minus 1. Okay, so this light blue part, is actually an sk minus 1 times an sn minus k minus 1 times some interval 0 to epsilon. And again, I'm squishing the same interval 0 to epsilon. Okay, but again, you know, one more time, if this is a little confusing, you can just take the picture that I'm giving you, which is the case k equals 1 and n equals 2. Okay, so after I do these two quotients, then the point is that maybe I can write this as an exercise that when I look at x a minus epsilon union h union r, and I quotient by this equivalence relation, this is homeomorphic to what I already had. So this doesn't change the homeomorphism type. Moreover, well, let me just draw the picture again. So what is this picture? Let me draw the picture one more time. So here's H, and here's R. So after this equivalence relation, what I actually get is I get something like this. So this guy, which is what I had before, and then I get the H that goes like this. This is the quotient. And the R disappeared because the R got squished to something that was already in X A minus epsilon. So this part here, this red, is X A minus epsilon, and this part here is your H quotiented by the equivalence relation, if you want. Okay. Again, if you want to concentrate on the case k equals 1, n equals 2, that's completely fine. And I'm saying homeomorphic because this union here has a corner. But up to a homeomorphism, you know, the homeomorphism doesn't care about the corners. And then now there's one more procedure, which is called smoothening the corners. So smoothening corners. So this is a procedure that you can always do when you have a corner. So when you have a corner of a manifold, one thing you can always do is you can look, you know this is homeomorphic to something without a corner. And you can just say, well, now instead of looking at a chart that takes this to an open set of the first quadrant, I first apply this homeomorphism, and then I take a chart from here. So you change the charts in the neighborhood of this point. So you throw away all the charts that are corner charts, and you replace them by charts that are given by, first you take the homeomorphism to a genuine boundary point, and then you take charts out of this point. So this is called smoothening corners. I don't want to get into it very much, but if you are just in this dimension, you know, if you're in the case k equals 1 and n equals 2, really what you have is, instead of looking at this of charts of this, you look at all the charts that take the corner point to something like this, and you compose with a homeomorphism that kind of opens it up. And these are the new charts. So this procedure smoothens corners of this manifold with corners. And the point now is actually, if you take your X A minus epsilon and you take the union with this H tilde, this is a manifold with corners, but after you smoothen the corners, after smoothening the corners, this is diffeomorphic to X A plus epsilon. Okay, so let me draw this picture one more time. So here is your X A minus epsilon. And when you go through your critical level, what actually you're doing is you're taking this H tilde and you're gluing it. And then you smoothen the corners. And this figure is your X A plus epsilon. Okay. All right, so before I open for questions, let me just describe what this H tilde is. So this H tilde is just your H quotiented by this equivalence relation, and the equivalence relation just identifies these points here along the flow. Like here's the definition of the equivalence relation. So what you do is basically you take these points that, this blue piece here of H was just an Sk times an Sn minus k minus 1 times the interval, and you just kind of erase the interval part. So now when you squish that, all that you actually are left with is you're left with the product of this part with this part. So maybe I should say this is an exercise, is to prove that this H tilde is equal or diffeomorphic to a ball n times, a ball k times a ball in n minus k. So here is your ball k, and here is your ball n minus k. Okay, so this basically all of this you can do if you carefully look at the function a minus norm of x squared plus norm of y squared. All of this is local. The only part that's not local is looking at r. But that's what I said, because of the flow of the gradient, you can see it's a product, and you kind of squish the product to nothing. You just kind of retract it to a minus epsilon, and then you get this. So the, bk. So basically the conclusion is if A is the image of a critical point and the index of this critical point is k, then how do you go from a minus epsilon to a plus epsilon, or a plus epsilon is just going to be a minus epsilon union with something with a bk times a bn minus k. But there's this union actually is a union where you identified something. So what do you identify? You identify, so this phi is the identification, and you identify just part of the boundary of bk times bn minus k. So if this is your bk times bn minus k, see, you don't identify the whole boundary, you identify a piece of the boundary. This piece right here. And this piece, you can think of it as sort of phi is an embedding from sk times b n minus k into the boundary of x a minus epsilon. So this is an embedding. So that's the identification. That's the gluing map. Okay. The next thing I'm going to do is I'm going to do some examples before we finish the class. But before that, questions. Any questions?
You had a homeomorphism,
Yeah.
and then you smoothen the corners, and you got a diffio. But
Yeah.
you had to pass by a homeomorphism.
Not really. You don't. If you smoothen the corners, you can go directly to a diffeomorphism. I mean, it's a diffeomorphism except at these corners.
Okay.
So it's just a subtlety. Yeah.
Okay. Thank you.
It's not like it's a homeomorphism everywhere, and you have this very complicated behavior at many points. You just have, it's just not smooth at the corners, but everywhere else you can make it, it's actually smooth. And
Okay.
if you smoothen the corners, then it's smooth there too. Other questions? Maybe you want to see the examples first. Let's go through the examples. The examples might be enlightening. So let's go again to the case n equals 2, k equals 1. So let's go to our favorite Morse function. And let's see what's happening when you cross the first critical point, the first index 1 critical point. Okay, so you start, with something that looks like this. And then you end with something like this. So what I want to show you is let's try to understand this, this guy. So this is the pre-image of a minus epsilon, a plus epsilon. Okay, so here, when you look at a neighborhood of the critical point, then actually what you have is you have a figure like this. So this is my blue, and you can actually see the handle right here. So say this is my blue. But when you look at a neighborhood here, you have green, green, light green, light green. Then you have the point right in the middle, and then you have these flows. Okay, so I'm using the same colors. And the pink is this thing here in the middle. Okay, so this pink is what I called H, and what I'm going to draw in red is what I'm calling R. Okay, so the procedure that I described is, well, this R, you just shrink it, you shrink this direction, the 0, 1 direction to a point. So you shrink this guy, all of this, and then what you're left with is you're really left with just this green and then the pink stripe. So over here in this picture, what happens when you do this is you have this disk and you just have this pink band. Okay, that's what happens when you shrink. And what I said is that, if you just add this pink band, then you actually will have corners. Here you have 4 corners. But if you smoothen the corners, that means you just change the smooth structure at the corners so that these are now like a smooth part of the boundary. Then you actually have something like this, which is exactly diffeomorphic to this surface. Okay? So does everybody see this? This is kind of something you really have to see.
Na primeira parte da figura acima, qual o procedimento que soma com a parte verde clara?
Essa parte aqui?
É.
O procedimento é basicamente você olhar para... Tirando a parte rosa, né? Essa parte daqui, né? Que não é verde claro, é a parte vermelha, né? Essa parte vermelha, esse R, ele é alguma curva vezes o intervalo, sei lá, 0, 2 epsilon. O que eu estou fazendo é, eu estou fazendo o quociente e removendo essa parte daqui. Então, assim, eu estou identificando todos os pontos ao longo do fluxo. Então, essas linhas aqui, eu estou identificando essas linhas todas, então elas vão virar um ponto.
Tá, agora eu vi a figura de baixo.
Você viu? Essa parte rosa daqui de cima é essa parte rosa daqui.
Uhum.
Então, essa parte aqui não morre, essa parte aqui continua.
Sim.
O que morre é o verde que sai daqui e continua. Quer dizer, ele não morre, ele é identificado com verde escuro. Ele é identificado com esse verde escuro daqui. Certo? Então, esse verde claro daqui é identificado com esse verde escuro. E essa parte, e esse vermelho daqui morre. Okay? So that's the procedure. So this is quite remarkable because this is describing what you need to do to be able to, what the change of topology is when you go through a critical point or through a critical value. Okay. So let's continue in our example here. So in our example, when we go through the minimum, what happens is you have a disk. You had nothing, and now you have a disk. So when you go through the first index 1 critical point, through the critical value corresponding to that, what happens is you attach what's called a one handle. So one handle is something like this. Okay, so then you know, this is the same as doing this. This is diffeomorphic to this figure here. And then now, when you go through the next critical value, you attach another one handle. So you attach another thing like this. So you're going to attach another thing like this. And this, again, you know, smoothen the corners. And that's the same as this figure. And, you know, to see that, you know, this is the same as this figure, it's just the same procedure here. You kind of shrink this color, this kind of color neighborhood. And then you get to this. And then the last procedure is you just put a disk on top. You cap it with a disk. And then from here, you cap it with a disk corresponding to the maximum. Okay, so let's, streamline this. So what is the process of attaching handles? The process is very simple if we understand this. I'm doing the thing backwards. So I guess I could have said this is attaching handles and going through a critical value is the same as attaching a handle, but I wanted to kind of deduce what the handle is. So a handle is the following. So say you're in n dimensions, so say x, say that we fix n, which is the dimension of the manifold. So a k handle is basically just the bk times bn minus k. So actually this is homeomorphic to bn, so like in terms of homeomorphisms, it doesn't really change very much, but the point is the attaching map. So an attaching map is an embedding that goes from sk minus 1 times bn minus k to, say, x a minus epsilon. You can do this for any manifold with boundary. So if you have a manifold with boundary, this x a minus epsilon, for example, you can attach a k handle. So how do you attach a k handle? Well, first you have to have an attaching map, which is an embedding of a part of this boundary to the boundary of the manifold you want to attach. And then the attached manifold will be a x a minus epsilon union your handle, but the union over using the attaching map. So that's the same as you look at the disjoint union and you quotient by the map where x is identified with phi of x. Okay, so again, let's look at the examples of the spheres, because I think that's so let's look at the examples of surfaces. So if I have, say I have this disk here, a one handle will be a B1 times B1 attached along an S0 times B1. So I have to find an S0 times B1 on the boundary of my surface. So here's my S0 times B1. And then now I glue a B1 times B1 along that. So now I glue my B1 times B1 along that. This is it. And then I have to smoothen the corners. So I guess the theorem, as you can call it like that, which we basically proved now with this argument, is that x a minus epsilon is obtained from x a minus epsilon by attaching a k handle. Okay. All right. So that's basically the procedure. You have a manifold, a closed manifold, so that gives, when you pick a Morse function on it, where you suppose that all the critical values correspond to unique critical points, then how do you reconstruct the manifold? As you go through every critical value, you're attaching a k handle where k is the index of the critical point. Okay, and you always, the first one to attach is always a zero handle, which is a ball. And then the last one to attach is also a ball, which is an n handle, but it's a ball that's glued along its boundary. So a zero handle is a ball that's glued to nothing, and an n handle is a ball that's glued along its boundary. Okay, so that's the general procedure. Let me just emphasize this. So what's the zero handle? A zero handle is B0 times Bn. So that's just it's diffeomorphic to Bn. But it's attached along, so the boundary of B0, so it would be S minus 1 So it's nothing along the empty set. So as we said in the previous examples, when you have a zero, index 0 critical point, then you just have a new ball that appears. So you just take the disjoint union with a ball. But an n handle, like a maximum dimensional handle, is a Bn times B0, which is also diffeomorphic to a Bn, but it's attached along Sn-1 times B0. So you just have to find an Sn-1 on the boundary, and you attach it on that. So it's a little tricky. You can't always attach a handle to something you had before. You need this attaching map, which is this embedding. Okay? All right, so this is kind of the theory of handle attachment and handle decomposition. So next time, we're going to look at more examples and apply this to classify surfaces. And as a bonus, we can classify one manifolds too. Okay, let's stop here.